Okay, good. So, okay, great. So, welcome to the RIKEN INSAIT joint workshop. We are going to have a series of talks here from INSAIT and from researchers at RIKEN. And yeah, it's again great pleasure to have Professor Masashi Sugiyama here, who is the director of the RIKEN AI Institute. He gave a talk yesterday. And yeah, we're hoping to strike some collaborations with researchers at RIKEN and further work and exchanges and so on. So I think, yeah, maybe say a few words.
Yeah. Okay, good morning in Bulgaria and good afternoon in Japan. So welcome to the joint workshop here. So it's my great pleasure to be in Bulgaria for the first time. And already I gave a talk yesterday and we had very nice discussion. And this is kind of day 2 for me. But so today, so after the workshop, we plan to have more discussion. So it's great to have like 3 speakers from INSAIT and also 3 speakers from RIKEN AIP, and hope that we can find common topics and have nice discussion in the afternoon. Okay, let's start.
Okay, great. So so we have the program. So we are a little late. We apologize, but we'll keep the initial high-level presentation short. Most people here know it, so it's mostly for the remote people who are in Japan. So let me tell you just a couple of words about INSAIT in a couple of minutes, and then we can start with the technical presentation. Danda, you have access to the Zoom, right? To the links. Okay. All right. So I mean, you guys here know it, but I think our guests don't. So my name is Martin Vechev. I'm the scientific director of INSAIT. I'm also a full professor at ETH Zurich. And so I'll tell you quickly about INSAIT because some of you don't know. So it's a strategic government project which was funded by the government with around $100 million, about 90 million euro for a period of 10 years. And it also has attracted funding from industry like Google, DeepMind, VMware, AWS, and others in the range of $50 million, a little more now. So the idea of INSAIT is to create a world-class research institution, the first such institution in Eastern Europe. In many ways, similar to how RIKEN is established as a world-class research institution now in Japan over many years now. So INSAIT is structured in the following way. There is a scientific director, myself. There is also Borislav Petrov, who is an executive director, and there are supervisory and advisory boards. Supervisory board is responsible for taking all the decisions and insight and approving the decisions. And the advisory board also participates in various decision-making processes. So these are a bunch of really world-renowned scientists from different universities around the world: US, Switzerland, Israel, and and Austria, also Google. So that's the structure of INSAIT. Just a couple of accomplishments over the last year. I will not list them all, just a couple. So INSAIT became the first institution in Eastern Europe to join ELIS. ELIS is the most prestigious network community distributed lab, if you like, in Europe for advancing AI research and innovation. So a bunch of world-class universities are already there, like Cambridge, Oxford, ETH, and others. And our INSAIT is also part of this. So it comes with many benefits: joint PhD programs, resources, workshops, and so on and so forth. So it's actually the only one in Eastern Europe that's created, as you can see from the map. It's a long process to be selected there. It's like a year and a half or so. So that's as far as structurally. There is. Oh, did I include other things? Oh yeah. So this is. These are some of the areas currently at INSAIT that people are working on. INSAIT is still bootstrapping, so we have about 12, 13 PhD students. Some are joining now, and several faculty which we hired in the first actually hiring cycle, which are going to give talks today, short technical talks. So these are the general areas that INSAIT works in. So around trustworthy, reliable AI, which means building machine learning models with guarantees more generally, assessing the reliability, security of machine learning models. So research here includes things like randomized smoothing, convex approximations, verification of machine learning models, neural networks, also federated learning, game theory, differential privacy, things like this. You'll hear a little bit more today from Dr. Nikola Konstantinov on some of these topics. Not all, we are exploring quite a range of topics here, also jointly with ETH, but also some which are just at INSAIT. We're working on quantum computing and specifically on making quantum computers easier to program by developing new programming languages, new verification tools, analysis tools, new simulators. So that's also quite exciting, and we are, what it seems, set to expand this in the next hiring cycles in the intersection of quantum machine learning and vision. We also have quite a bit of research going on in computer vision. You'll hear talks on this intersection of computer vision and machine perception and natural language processing with robotics. We have a partnership with Toyota Research as well, and joint projects there. And there is some work going on now in foundational models and building various models, and we are increasingly going to be working in that space, both language models, but also models for vision data. So this is actually quite exciting. Research is happening, world-class research at INSAIT. So a couple of things on the research side. So INSAIT had the first papers published, faculty at INSAIT, ICCV, it's the top conference in computer vision, and EURIPS, which many of you know. So these are actually the first papers that were published out of Bulgaria in the history. So that's kind of nice. So also INSAIT is doing research, world-class research, but also very interested in creating deep tech companies based on that research. So recently, a researcher at INSAIT created a deep tech company in the intersection of GPT, foundational models, and gaming, where the idea is to leverage GPT capabilities for generating code to customize games. So they raised money, and it was on the TechCrunch, which is the main media of for talking about startups in the world. So this is quite exciting. All right, so they are actually planning to open an office next to INSAIT now that they raised. So a lot of nice research problems out of these deep tech companies as well. Okay, I think the connection to Japan is very exciting for us, and we are very much looking forward to strengthening this connection in a meaningful way in terms of research, in terms of partnerships. We had the visit of the Japanese Minister of Economy on the 5th of May this year, and yeah, it's a bunch of representatives of the Bulgarian tech ecosystem and Japanese companies like Murata and NEC and others participate in the meeting. And we have ongoing discussion with the ministry for next steps. So we are quite excited now to strengthen these connections. Okay, so that's all I wanted to tell you. Just a couple of words about INSAIT for those who don't know much about it. INSAIT started, about a year and a half ago, but already is moving very well. And yeah, we are creating links, doing research, and hoping to do great work. So the workshop today is part of this strategy, and we're very excited to have again Professor Masashi Sugiyama at INSAIT to discuss research, to discuss collaborations, to start joint papers, projects, and so on. So that's it from me.
Good morning here and good afternoon in Japan. I am Danda Paudel, faculty here at INSAIT, also partially still working at ETH. Today, I will be talking about visual modeling of indoor scenes. My background is computer vision. Today is mostly about the indoor scenes, talking about both the challenges and opportunities. If you have any questions anytime, feel free to interrupt. Talk is expected to be about only 20 minutes. Okay, just like now, most of the time we are indoors. All right, so sorry for that. So yeah, so almost 87% of our time we spend indoors. And almost about 85 or even more of images in the internet ever taken are of indoors or of involving human-made structures. So interesting part is that human, when they make structures, they have structures, right? So unfortunately, though, that when we are trying to play with the indoor scenes, all right, indoor scenes, when you are trying to, let's say, this example of reconstructing scenes, this outdoor reconstruction that we obtained was rather easy. And obtaining indoor, all this particular case, we chose an easy example of full of texture. But unfortunately, you cannot see indoor and outdoor at the same time. That brings pretty big problem in computer vision when you are trying to unify indoor and outdoor. Even in these particular, what we call easy examples, in the indoor, the reconstruction is not satisfactory, mostly because either there is nothing, just wall, or there's too much of clutter, or maybe not clutter. We are quite sensitive to tiny objects indoors. Therefore, reconstructions or understanding may also require quite a lot of details. So does the reconstructions. Altogether, visual modeling of indoor happens to be difficult, but in one way, if you see that indoor scene, they actually exhibit strong structural regularities, and they are mostly flat or largely flat. And they have, you have lots of prior about how the indoor should look like, because it's been designed and made by human, right? That should actually give us good prior about getting things done right, because larger the prior, easier the problem should be. Unfortunately, such kind of lack of texture in vision happens to be a bigger problem, both for reconstruction as well as understanding. That, for example, if your robot is stuck against a wall, it may just know it's a wall, but it's very, very difficult to know where in the building you are, because you are looking at the wall. So this poses big problem in the indoor visual modeling. This is one of the reconstruction that we obtained at the lab at ETH back in 2019, where the blue part with the white lining is basically the floor plan. And you can see this is the reconstruction that we could obtain best at that time using the state-of-the-art method for 3D reconstruction, which I would consider it to be poor. Mostly because the repetitive structures and texture-less regions really makes it difficult to reconstruct. All right, today's talk outline is going to be about reconstruction. Nowadays, reconstruction largely done using neural radiance fields, which I will further explore later on. We'll talk about the structure of the indoor scenes, because indoor scenes do have a structure, better have structure. They could be very much useful for many applications in indoors. When you talk about indoors, there are furnitures and there are humans. They become vital thing to take care or look for. And one particular application of augmented reality in indoor scenes. These are 4 different works from 19 to 23, published at different venue. I will largely focus on the recent work at, this is also one of the first published works from INSAIT on this neural radiance field modeling. In today's talk, go a little bit more in details, and then zoom out to summarize different parts before we proceed further. So, neural radiance field is a way of representing 3D scenes together with the both geometry and the color or the texture. The way it's been done is implicitly. It means you may have heard about representing scenes, 3D structures using point cloud, maybe using 3D meshes, and recently may also have heard about using 3D structures using neural networks. Basically, the weight of the neural networks somehow becomes the representation of the 3D. That in loosely speaking, you do it by overfitting your neural network onto the 3D structure. Thereby, at the end, you just need the weights of a neural network, and you don't need anything else to represent 3D. The weight of that neural network can be supervised using multiple images of the same scene in the framework of so-called NURF, or neural radiance fields optimization. This is a common technique, very popular in computer vision for the last 3 years. And in these settings, we would like to do 3D reconstruction or 3D representation of the indoor scenes using this NURF for indoors. Here, this is the baseline NURF, state-of-the-art method a year back. Now things getting better, of course. You can see that there are floating artifacts, which ideally you would not like them to be. This particular video is the rendering of the representation. If it looks like the realistic video, it means the representation is good. So these NURF techniques, they seem to struggle quite a lot in difficult indoor scenes, especially when you are trying to reconstruct indoor scenes using sparse set of images. So in this particular work, and in this particular talk, I'm going to talk about is a very simple prior of Manhattan world. That when you build buildings, especially indoors, you try to make your floor rather or better flat. Ceilings mostly flat, walls mostly vertical, and 2 walls perpendicular to each other. These are the structures that are embedded in the design most of the time, of course, not all the time. And this is called the Manhattan world assumption, where things are perpendicular to each other. This is the prior of the indoor scenes that we are going to embed in the NURF framework. What we basically do is we compute the normals of the scene. Here, different colors. Well, here the triangles are the set of 3 points from which we compute the normals. We wish to cluster them in a way that it forms 3 clusters for, well, if we correct the signs, because we assume, let's say, the floor and the ceiling have the same normal after flipping the sign, that you can largely do by knowing where your camera is, because your camera has to be on the visual side of the plane from the ceiling as well as the floor. That way you can always know, okay, you can basically correct the sign of the ceiling and the floor or opposite planes. That way, what we are looking for in Manhattan world assumption is 3 clusters of 3 clusters of normals which are orthogonal to each other. That would help me to basically make a box, right? Make a box. And what we do in this particular work is when the camera is looking onto a surface, we select 3 points. And once you have 3 points, it's easy to basically compute the normal of that of a plane passing through those 3 points. That's how one can obtain a normal, simple equation. And then we want to cluster this set of normals obtained from everywhere, such that they are these N1, N2, and N3 are the centroid of 3 major clusters that we obtain after clustering. And we want them to be orthogonal to each other. That just becomes one of the laws in neural network training. At the same time, here, other eyes are the normals belonging to that clusters. It means once you found the center, you can also say that, okay, so other normals nearby, they better be having only one normal, because you don't want to have any variations. So basically, you're just trying to have the tight clusters for at least 3 of them. Rest, we let them be free. these are the two losses that we introduce in the standard neural audience framework training. This is the pipeline. So here, this image loss is standard loss that's been used for NORF training. Here, in this particular work, we compute the normal, cluster them, impose those losses, orthogonality by these two derived losses, and just use these two additional loss to train the network. This is just the algorithm to summarize. And conduct the experiments on our own post-process data. This is publicly available data, but never used for the NOR pipeline. Before that, we prepare this data and then run the experiments, one on the baseline on the left that I showed you before, one on the right, of course, not perfect, but you can see it's much better. So partial to summarize, so far I said, is most of the time we are indoor. Most of the images or videos taken indoor. And we have the strong priors about them. And if we exploit them well, then these difficult problems, they tend to be getting easier. On the contrary, if we don't use them, they seem to make actually problems that the indoor scenes not having sufficient texture and having flat structures are actually the problem for many computer vision algorithms. These are some numerical results that this is the hour method, where higher the PSNR means better. That the baseline would be 25. It improves 2 PSNR almost. And then normals is improves significantly. And these are the other methods in the literature which you compare. And this is just a comparison on larger data set. Here, we show that this is the PSNR obtained by the baseline method. Lower the PSNR means harder the scenes. Higher the PSNR means easier the scenes for the baseline. And the percentage improvements in these settings for different data sets is that when the scene is harder, the Manhattan prior that proposed in this particular paper indeed improves quite a lot. When the scene is not that hard, is already mostly solved by the baseline, it doesn't improve much. All right, that was the first part of the talk about exploiting Manhattan prior to model weighted NOR for indoor scenes. Now zooming slightly more into the things inside indoor is the furnitures, let's say, that these furnitures have shared shapes. You can run some form of PCA, let's say, that they do live in some kind of PCA space in the point cloud, any kind of structures you represent. And also human. They also have common structures. Somehow humans' common structure is slightly different than the chair's common structures, mostly because each instance of human can deform, each instance of chair generally doesn't deform, right? Then, but again, that humans repeat, the structures of the human repeat, like largely speaking, structure of the chairs repeat, then isn't that, or shouldn't that already be sufficient self-supervised signal given enough instances of human and the chairs to learn from, right? Especially in the indoor scenes, that's kind of prior that you have. And this is one of the work 2020 on learning key points on humans and on the furnitures that we use to learn the interesting points on 3D using this low rank prior of indoor structures, not only indoor structure, but we largely conduct experiments indoor structures of different furnitures and human beings. The question it brings down to is that what level of self-supervision can be obtained from scene-aware modeling, where you have very, very weak levels, of like, this is indoor, right? And that already should allow you to use priors in some weak sense to make self-supervised methods. This is one of such examples. So I'm coming slightly towards the application. This particular application, we were working with Huawei smartphones back in 2018-19, where they were trying to help human to navigate indoors. So to help human to navigate indoors, you cannot really use GPS because indoor GPS is bad. So you need to know where you are, but you don't need to know precisely where you are because human can figure out. You just need to know in the topology. Somehow you should be able to localize them roughly about, let's say, in the floor plan, that you should be going somewhere straight for 3 rooms and then take an elevator and stuff like that. Right? That's the kind of problem that we were dealing with in the augmented reality settings. Maybe I play the video, will make it easier. Here, a user takes a picture. This is actually picture taken in the same scene that I showed previously, that it was difficult to perform proper 3D reconstruction in the lab at ETS. This picture is taken, and the picture goes into the cloud and does some form of topological reasoning and queries another picture on which the augmentation is done, so that user knows, okay, if user goes out of this room, take left, will reach to Professor Luke Bangul's office. If you go to the right, you go to the coffee room. So eventually, you don't need to precisely localize your image, especially if you are trying to help, that you have taken in the exact scene. Instead, you just need to know roughly where the image might have taken, and then any instruction that user might be interested to feed back. In this particular example, that we even didn't augment the same image. We rather provided the another image nearby that's been augmented for the task the user might be interested. Similarly, the augmentation on the floor plan, that for the robots, maybe it would have been different because robots may also need to do obstacle avoidance planning and so on and so forth. Whereas for human, you don't really have to, help them for obstacle avoidance generally, or for the navigation. You just have to tell them general directions in the topological scale, in the general topology. So in the indoor settings, if you are trying to help human need minor guidance at topology level. Then we also do another applications. Okay, that comment was more about these different applications. I will skip that now. To summarize that, on the previously I talked about the modeling aspect, 3D modeling aspects of the indoors, and now understanding aspects of the indoor could also be not only for the indoors, but generally speaking, could also be task aware, with one particular highlighted example that if you're trying to help human, you don't have to be as fine-grained as you're trying to help robots. All right, now I will try to go towards more of the summarization of what we actually now doing at INSAIT. In the indoor settings, our largely focus is to understand making this spatial awareness, something also called spatial AI, of the indoor scenes, not only understanding images, because if you can actually give your images to GPT-4 and it can actually answer your questions, that you would like to do something similar to your 3D scenes. So somehow feeding the whole 3D scenes around and making the task plans or asking questions about it. This is one image that I borrowed from the workshop on language for 3D vision from ICCB 23. This becoming quite a hot topic to be able to feed 3D models onto large language models or large language vision models and have a dialogue about different kind of questions one user might have. So in these settings at INSAIT, we are interested in two kinds of applications. One in the museum, indoor again, one in the kitchen. In the museum, we are interested on having personal AI assistant, where you can have this vision language-based interactions. In the kitchen, well, ideally, we like our robots to cook food for us. To start would help us in the kitchen when we are cooking. These are the two ongoing works that we have. For the kitchen robot, we actually do have robot we started to play with from Toyota. This is HSR robot, some of you may already know. We actually have a fully furnished or on the process fully furnished kitchen, actually built only for this robot or only for the project. This is a fully functioning kitchen that we have here. And that's INSAIT kitchen at INSAIT, and INSAIT at the museum. We are going at 2 o'clock today. Thank you very much.
I don't know if there are questions on the channel, or people can ask questions from there. You can, but I mean, there's some chat.
Yes.
What? Oh, it's for the discussion. Okay. Oh, there's.
Yeah, so the floaters, the first section of your talk, are because mostly the images we're using are sparse within there. So how does intuitively the Manhattan assumption help? Because from the demo, it showed that you have less floaters after assuming the Manhattan. How does that help with why we have floaters if you don't assume the Manhattan work?
So we are trying to cluster the normals, right? If you compute the normals on the floaters, there will not be the particular properties that we are looking for. So then we are trying to push them gradually, little by little, and eventually it takes, your loss becomes much more higher if you use if the floaters are there. It doesn't take much to minimize the loss. It's a small trade-off in loss, at least the photometric loss, to respect that particular constraint. So basically the floaters normals are more arbitrary and everywhere. They don't really respect the Manhattan prior. Not sure if they are. Yes, please.
It's about Manhattan prior. How reasonable is it? Because in general, we see a lot of clutter on the scene, right? A lot of the furniture is not actually straight on.
Yeah.
And also top floors, when they go to scan, it's usually leaving walls as well.
Yeah.
So even with straight walls, you are unlikely to find from the scene the actual normals of the wall, right?
Yeah, I mean, what we do is actually we do have 20 clusters. Out of 20, we encourage 3 largest ones to be orthogonal to each other. So you just can have many more clusters, right? So we just try to say if there are 3 clusters which are large enough and also orthogonal, right? So coming back to your question, actually, floors are almost always flat. So is the table. Otherwise, I cannot put my coffee on the table, right? There are really strict constraints often that the horizontal constraint is met. Often, the vertical constraints may not meet. I mean, sometimes, right? Especially artistically rich designs. Let's say if you go to Gaudi's design, then yeah, sure, the guy Gaudi doesn't really follow this Manhattan assumption, right? But only on those special cases. But if you just say statistically speaking, then you can largely because Manhattan is not only about the box, actually. Manhattan is really about having 6 parallel planes, three sets of parallel planes, right? For example, this table, actually part of the floor in the normals, and it still respects the Manhattan prior, right? Such kind of parallel structures, they do, because this is parallel to the chair's surface and also the ground and also the ceilings, right? Such kind of structures do happen in modern design, at least.
We should probably take it offline because we are way late and there's many speakers waiting. So maybe continue after. Yeah.
Okay, thank you for the introduction. So I'm Naoto from RIKEN AIP and also the University of Tokyo. So today's talk is about imaging and vision from space, and our group work on the intersection between computer vision and remote sensing. So we mainly work on 3 broader topics. One is image acquisition. So we want to get high quality imagery from space, for example, denoising or super resolution or compressive sensing. Everything is about inverse imaging problems. And the second part is image understanding, either semantic segmentation or 3D reconstruction. And by using these techniques, we try to tackle some real-world challenges like disaster management, environmental monitoring, and agriculture. And in the bottom of this slide, I'm showing some examples of inverse imaging problems on the left-hand side. And at the middle, this is about semantic segmentation, pixel-wise classification. And on the right-hand side, this is one particular application of carbon stock estimation. So today, since the time is limited, I want to introduce 3 examples, one for each of these broad topics. So the first one is about automated mapping for everyone. So it is about, mostly the contribution is about data set construction. So last year we have developed the benchmark data set for global sub-meter level land cover mapping named Open Earth Map. So this is, the task is semantic segmentation, and the input imagery is a very high resolution sub-meter level aerial image or satellite imagery. So since in this domain, due to security reasons, there is a strict data policy restriction. So the data set acquired from space at very high resolution cannot be publicly distributed. So because of this, there was no benchmark data set for land cover mapping at sub-meter level. So we somehow addressed this issue so that everyone can map high resolution imagery if someone get imagery. So the model that the model trained on our Open Earth Map data works very well any place on this globe. And this is an example sampled from Zanzibar, Tanzania. So this kind of high resolution imagery can be, this is the prediction of our model. Of course, this data is not included in the data. And this another example is from the one from Ecuador. The image quality is a little bit worse, but still we can see where is building, where is road, where is agriculture field and water, rangeland and bareland, and so on. And this imagery is from Japan, and particularly on top right-hand side here, this is the campus where I'm working on. So there are many, many small buildings, as you can see on the left-hand side. And our model can predict, as you can see, quite nice prediction, discriminating different classes. And I also downloaded images from Sofia, Bulgaria, 2 days ago to see how our model works. And this image is relatively nice image. So of course the model works. It's not perfect, but it's working anywhere on this globe. So what we have done is there are already many benchmark data sets for example, for building detection. But if we look at the distribution of the data, so please look at some marks, except for having light blue color. So these are XBD or INRIA, OpenCity, AI, SpaceNet, and so on. So these are already existing benchmark data, mainly for building detection. So we found that mostly existing data sets are coming from Europe or North America. So the model trained on these data set works pretty well in Europe and North America, but it doesn't work in Africa or Asia or South America. So we wanted to solve this problem because it's really not fair if the model doesn't work in our country. So we try to collect open data, either mostly aerial data from those data poor regions and countries, and then collected in total 5,000 images. It's not very large scale, but in our domain, this is the first data set covering many countries, like 44 countries and almost 100 different regions. And after collecting images, this is the time-consuming part. We labeled each image with 8 different classes, like buildings, agriculture, water, tree, road, and developed space, rangeland, and bareland. So here I'm listing 7 examples sampled from different regions. So you can see the annotation is very detailed, and we spent some time to make sure about the quality. And this is not something that only we want to do. Many institutions, space agencies, and companies, they want to do this, but due to the data policy issue, there was no public benchmark data to enable the model to work everywhere on this planet. So here on the right-hand side, this is the plot spanning characterizing the benchmark data sets with respect to geographic diversity and also annotation quality. How detailed is the annotation? So for example, the Dynamic EarthNet, this is from German Aerospace Center, DLR, where I also worked for 2 years. And this XBD, this is actually coming from Ministry of Defense from US. And LoveDA, this is from Wuhan University in China, which is #1 university in China for remote sensing. And this big globe is a little bit old, but this is from Meta, Facebook at that time. So you can see our OpenMars map is much better in terms of geographic diversity and annotation quality. So it makes a difference for generalization, particularly for out-of-sample distribution. So if we put some images, which is not included, none of those benchmark data. On the right, left-hand side, this is the input image. And the second column is the reference, and the third column is the prediction result of the model trained on our data, OpenEarthMap data. And the 3 columns on the right-hand side is the prediction results of the models trained on existing data sets. So please note that the model used for those predictions are all the same, like UNet using some efficient net as backbone. So the difference just comes from the data. So you can see that compared to those existing data sets, our predictions are much better and accurate. And the model works without any tuning. For example, if something happened, if disaster happened, for example, this year, Turkey, Syria, earthquake happened. And at that time, for this kind of disaster, space agencies provide imageries for free. So we applied and made a mapping. So model still works without any tuning. And it was not really possible before. Usually, some sort of tuning was required, but currently the model is working pretty well. And you can see comparing between pre-disaster and post-disaster images, the prediction results indicate the understanding about whether buildings or road exist or not. So disaster response was, it's one of the most important applications our group is working on. So we worked on this kind of OpenEarthMap data to create some sort of land cover map to show the semantic changes as soon as possible if some disaster happened. So the second topic is about disaster management and disaster response. So in the last 5 years, we tried to work closely with disaster management experts as well as space agency people. And here are a few examples of what we have provided to the disaster management agencies, like flood mapping or debris flow mapping or some building damage mapping. It's not research. It was all done as a activities part of the disaster response. So something happened and we got data and we try to provide these maps as soon as possible to the space agencies and disaster management experts. And we are trying to build up the system that can automatically or semi-automatically create useful information to understand some changes after natural disasters for very large area. If the area is very small, satellite may not be needed, but when something happens in a very large area, the satellite is very effective. And here I want to show you the example. This is the very big typhoon named the Hagibis, happened in 2019, so 4 years ago. This is an optical imagery, Sentinel-2 imagery operated by European Space Agency. If the resolution is coarse, this image, 1 pixel is 10 meters, different from Open Earth map. The resolution is somehow meter level resolution. And in this case, data are all freely available thanks to the decision of EU. So here is the pre-disaster imagery, and here is the post-disaster imagery. So as you can see, optical imagery is actually measuring the reflectance, radiance reflected either on the land surface or atmosphere. So if there is any cloud, optical imagery is somehow useless. So in this case, we usually use, it's called the synthetic aperture radar, which try to use microwave. So this is an active sensor to this transmit microwave and then measuring the backscattering signals. So maybe you are not familiar with this kind of imagery. So those grayscale values are corresponding to the properties of the surface. For example, if there is water and then specular reflection happen, so synthetic aperture radar usually transmit the electromagnetic waves having some off-nadir angle. So when specular reflection happens and then no signal will come back to the sensor. So in this case, the pixel looks dark. And if there is something like grass or something, if some scattering happen and then it's a little bit brighter than black. And for forest or trees, if there is any structures and then multiple scattering or volume scattering happen, and so it could be even brighter than the grass. And when there is any man-made objects like houses or buildings, and then double reflection happens. So in this case, the image pixel looks very, very bright. So you can see urban area looks bright. So the advantage of this sensor is even if there is any cloud, we can acquire images. So it's a kind of all-weather condition sensing system, and even we don't need any sunlight. So you can see I'm switching pre and post disaster images, and you can see that the pixel values are changing. So if we look at the color composite imagery using pre and post disaster images for RGB, and then we can see that the flooded region have different colors. And by processing some simple image processing without any machine learning, we can predict, we can get some binary mask like flooded extent. So when we talk to some disaster expert and they 5 or 6 years ago, they requested, okay, this is better than nothing. But if some disaster like flooding happened, people want to know whether inundation depth was 50 centimeters or 3 meters. So they mean totally different level of damages on buildings. Or if some debris flow happen, for example, people want to know for the disaster relief activities, they want to know how much soil eroded where and how much soil accumulated in which areas. So in order to address this issue to be beyond this binary map, we have developed the technique to estimate some surface three-dimensional change. And this result is most probably the first prediction result of the maximum water level directly estimated from tinted aperture radar satellite data by using deep learning. And in Japan, disaster management is a very important application, and the government agency, the geospatial agency, is usually responsible for doing some flight campaign to take aerial photo and try to identify some flooded region annotation, and then try to estimate inundation depths. So such map is shown on the right-hand side. So our automated method could predict something consistent with the map that was made with a lot of human efforts on the right-hand side. So I want to briefly share the core idea. So the main idea is to combine remote sensing and numerical simulation and machine learning all together. So from remote sensing data, we can get some binary change map, but it's not possible to estimate some inundation depths or some topographic deformation due to debris flow, for example. And numerical simulation expert, they say, yeah, we can simulate anything. Yes, that's true. If they have some input data, they can simulate something. And by degrading three-dimensional change information, we can also get some binary change information. By changing some input or parameters, simulation can create a lot of different kinds of patterns, what kind of 3D changes can happen with what kind of scenario. But actually, it's very time-consuming to conduct a numerical simulation, which perfectly fits with the real phenomenon. For example, in order to perform this debris flow simulation, the simulator requires the input, the location of the starting point of debris flow as input. So such information is usually not really available at the beginning, which usually require some advanced technique to interpret the image, or in practice, it's all done by visual interpretation, so which is time consuming. And also changing parameters will change many things. So simulation is also not really helpful to give accurate 3D change information right after disaster. So we regarded those simulation data as the training data, and then try to make the regression model having binary change information and topographic data as input to predict three-dimensional change like water, maximum water level, or topographic deformation. And once this regression model is trained, and if something happened, and we just need to put the change map information to get what we wanted to obtain. So it's a kind of try to take advantage of both numerical simulation and remote sensing, which is actually sensing real phenomenon, and try to bridge these real data and synthetic data by machine learning. So here is a few examples of the debris flow mapping to show some proof of concept. So the middle image is the change detection result with some conventional image processing technique obtained from bitemporal remote sensing images. And on the right-hand side, this is the topographic deformation prediction result obtained by our approach. And we also collected some LiDAR data which measure the height information, and we confirmed There are some errors, but we confirmed that these distributions of blue and red pixels are responding to erosion and accumulation of the soil, and they are quite consistent with the LiDAR measurements. So this is the second topic, to try to respond and try to obtain the information that we cannot measure or that we cannot collect real training data. So we use numerical simulation to address this issue. And the last topic is about image acquisition. And in remote sensing, there are so many different sensors. It's not only RGB, but panchromatic imagery is usually high resolution, and we also have multispectral data or hyperspectral data, which is beyond our vision, observing near infrared or short wavelengths infrared range. And also, as I mentioned, there is also sensor using microwave, and also there are some thermal imaging or LiDAR point cloud data to measure the height information. So there are many diverse sensors and different projects, and different satellite projects usually have some trade-offs in the sensor specifications, like spatial resolution or temporal resolution or spectral resolution. So on the left-hand side, this is the plots of the different satellites projects spanned by spectral resolution and spatial resolution for horizontal and vertical axes. And you can see that the bottom right-hand side is what we want to obtain, but it's not possible because of the trade-off. So usually to increase resolution, either in spatial, temporal, or spectral, usually computational imaging plays a very key role. And synthetic aperture radar is the typical sensor that require computational imaging, which means the imaging system that assume computation to acquire the image. And pan-sharpening is also, probably most of you have seen some high-resolution satellite image, and most of them are pan-sharpened image, which is the kind of fusion-based super resolution to combine panchromatic image and low-resolution multispectral image to get high-resolution multispectral data. So fusion-based inverse imaging is one of also our focus, and we are working on how to make the technique to be able to handle any kinds of data, or we also work on compressive spectral imaging. And most state-of-the-art methods are usually supervised approach, but in our domain, collecting ground truths for super resolution is also very expensive. So we are also working on unsupervised approach. And today I want to share the work that we presented last year. It's about a cross-modal super resolution. So our motivation is to, let's fuse different resolution or multimodal images to enhance the lower resolution imagery. For example, as shown on the bottom left-hand side, we have low resolution height data and high resolution RGB image. And then what we want to obtain as output is high resolution height data. So we developed a technique to make it possible without any training data and also achieving state-of-the-art performance. So on the right-hand side, this is also common task in computer vision. So we also use depth and RGB image, guide and source low-resolution depth image. And the middle two examples are existing approaches. And you can see, for example, P2P showed some artifacts for non-relevant high-frequency components coming from guidance image. So compared to them, our approach, you can see, can create quite a reasonable prediction similar to ground truths. So the idea is very simple. So we try to use spatial filtering, which is a very, very basic component in image processing. So we name it as a mutual modulation. So after feature extraction from these two different modalities, we applied this mutual moderation, which actually calculates the correlation between feature vectors between guide and source images to calculate the weights for spatial filtering, and apply this filtering to source data feature map as well as the feature map obtained from guide image, and try to apply this spatial filtering in a mutual manner. So source to guide, long story short, this modulation has the role to enhance the spatial resolution of feature maps obtained from source image. And this guide to source moderation plays a role to eliminate unwanted spatial details which exist in the spatial feature maps obtained from guidance image. So by only applying this simple spatial filtering, the entire flow is actually working as an unsupervised manner, or let's say self-supervised manner, because there is no ground truth. So only supervision is the consistency loss between the source downgraded version of the prediction and the low resolution source imagery. So this idea works. We confirmed that the idea works with various combinations of different modalities like thermal or height or depths or infrared, so thermal infrared images. So that's all from my side, and thanks a lot. If there is any question, I'm happy to have discussion, and probably some topics are quite relevant to what you're working on. So I'm looking forward to any possible collaboration. Thank you so much.
Hi, everyone. So I will be talking about exploring a supervised learning for computer vision tasks. It will take around like 20-25 minutes. And this is basically the work that I did the last few years during my PhD, right? So first, I will give a brief introduction and the motivation why this is a relevant topic to explore. And then I will delve into 3 to 4 papers that we published at NeurIPS ECV and ICCV. And I will also try to summarize the key contributions, basically, and the key insights. Okay, so basically the topics that we will cover are scene understanding and self-supervised learning. Scene understanding basically involves modeling geometry, but also discovering different objects in the scene. And then I will primarily talk about self-supervised learning, which here we will say is basically the same as unsupervised learning, but actually there are some differences, but we will use these terms interchangeably. So basically here the goal is to learn meaningful representations or groups from large-scale datasets, right? If you look around us, we have a lot of cameras, we have a lot of images that we can leverage to train our models. For example, we have cameras in our cars, we have it in drones, of course, in our phones, etc. And we can apply these data to solve a lot of different vision tasks, ranging from autonomous driving to medical imaging. So here we aim to tackle self-supervised learning where we don't have any annotations available, so we need to rely on some sort of a prior or a pretext task to tackle this. And we will try to explore this in 4 different settings. We will start with general representation learning, where the goal is to learn general representations, and then we fine-tune them in just a small set of labels. And then we will tackle image classification, semantic object segmentation, and also even instance segmentation. So I assume that most of you are familiar with these different tasks. So first about self-supervised learning. So if you think about it, at scale, if you have a lot of data available, then you should be able to do some sort of a large-scale similarity search, right? If you look at here, a cat is much more similar to a dog or other cats than to giraffes. Giraffes have distinctive properties like a long neck. The texture is also completely different. So if we have a lot of data available, we should be able to leverage or at least find these properties from the data itself. So ideally, we can learn these discriminative groups or different groups that align with high-level objects. So again, the motivation is kind of straightforward, in my opinion. Something that I also find interesting is that these algorithms are not tied to a specific dataset taxonomy. So you basically want to learn a lot of information, not just the classes that are defined by the dataset by human. And in theory, you can apply this to many different types of problems, clustering problems, semi-supervised learning, transfer learning, and even multitask learning. That's one of the main advantages, that it's so versatile. Okay, what are some of the findings? So first, you need to rely on some sort of a pretext task. So it's a task for which you don't need any annotations. And the common setup here in general representation learning is that you first have a network, you train it with a certain pretext task, and ideally the representations encode high-level object information, especially in the later layers, you ideally want to encode objects, so high-level information. And in general representation learning, what you do then, you pre-train your model here, and then in the second stage, you fine-tune it. So it's basically the pre-training and fine-tuning paradigm that is extremely powerful if you have a model that you can leverage that encodes a lot of information about our visual world. Then the question arises, what kind of pretext model do you use? There are a bunch of different models that you can try to leverage. You can just try to leverage image-based contrastive models like SimCLR. That's one of the most basic ones. But you could use a more generative approach like masked image modeling. But we will primarily focus on SimCLR for now, for the primary reason because it's simple. And these contrastive methods lead to discriminative groups, or at least disentangled representation. So if you are interested in clustering or semi-supervised fine-tuning, then that's much easier, right? But of course, you could use these other models like multimodal models, right? If you have text available, or like at Meta, you have like Instagram dataset where you have noisy hashtags at scale. That's very valuable information. Okay, so we will try to leverage these kind of models. To briefly reiterate, if you take SimCLR, so basically what happens is you have an image, then you generate augmentations, right? For example, cropping, color jittering, etc. And then you pass these images through your model, and you generate a global feature. And what you say is that these features here on the left-hand side should be similar. You maximize the agreement between these two features, but at the same time, you also want to minimize this agreement with all the other images in your dataset. And since you have a very large dataset, this is a very valuable signal, because now this model has to encode a lot of detail about this image, because it has to discriminate this image from all the other images in your dataset. So that's why this is a very valuable, or at least a very powerful paradigm, this framework. Okay, but here, this is an ImageNet. Here we see examples on the ImageNet dataset. And as you can see, these are very iconic images. Like here we have an image of a dog, of a chair, etc. But what actually happens if you have more scene-centric datasets, like what is mostly the case in real life, for example, the Coco dataset, let's say. So that's something that we explored here. So what is the impact of these dataset biases on the final performance of these models, on these self-supervised models? And we also explored invariance learning. So can we improve the representations by adding additional invariances? Because that's actually an obvious direction to follow, right? So this SimCLR is actually derived from maximizing mutual information, because you want to maximize the mutual information between these two views. And we assume, basically, if we generate these augmentations, that there is always some sort of mutual information between these views. So this is actually a valuable learning signal. If you look at the expression, so the one that we used was this info NCE. It's basically a noise contrastive estimation, where you have in the numerator, you maximize the dot product between these two embeddings, so they are normalized, and then in the denominator you model the noise distribution basically based on all the negatives that we have from other images in the data set, right? Okay, so we found that for all these different kind of data set biases, so if you take into account MS Coco, Open Images, or Berkeley Deep Drive, which is domain-specific data set, this framework still works even on kind of, not that many images, like only 118,000. So that was an interesting observation. And then we tried to improve the representations by basically adding additional invariances. So one of the most interesting parts of this paper was that we were able to mine additional positives by exploring the data manifold, basically. So if you already have some structure in the representation, you can find additional positives by exploring its neighborhood, right, in this embedding space. And in this way, you can find additional positives, which you can incorporate in this loss that we just discussed. So the way we did it is by adding an additional loss term. And now you have a summation also over its nearest neighbors, right? So you also want to maximize the agreement there. Okay, and we found that on a lot of different downstream tasks and data sets, this actually boosts the performance. Okay, what was also interesting is that you can find these meaningful segments, right, from these models. So something that we tried was basically clustering the intermediate representations, and then you can find these objects, basically. So we cluster them, and then we generate one embedding for every region proposal, and we look for similar region proposals in our training dataset. So we can find planes, bicycles, etc. Now we go a step further, and we aim to tackle the classification task directly. We saw that prior works always try to do this in an end-to-end fashion, and they primarily latch onto low-level image cues like color or texture. So how can we tackle this? And we do this in a very similar fashion as we just discussed. So what we did was, again, relying on a pretext task, and then in the second step, we will train a clustering function based on the information that we can extract from this model. And we will use, again, nearest neighbors, because I'm a huge fan of nearest neighbors, actually. So for every image, we mine its nearest neighbor, right, from the training data set. And we saw that they actually align, or they are mostly correct. So at scale, again, this is a valuable signal to leverage. And then in the second step, we aim to produce consistent predictions, right, between an image and its neighbors. So the output of our model, the phi of x, is actually a probability distribution over multiple clusters. And you minimize, again, the dot product between an image and its nearest neighbors. And what this expression actually does is that you have consistent predictions, but also peaked, like the distribution also needs to go to 1. One of the downsides is if you only have this term, then it can just collapse. Everything can go to the same cluster, right? So you need to have some uniformity prior over the clusters, and you do that by maximizing the entropy of the clusters, basically. Okay, so this worked quite well. Also was quite popular at the time. So we were able to find these different clusters like airplanes, koalas on the image data set, etc. And they capture a lot of different backgrounds and viewpoints. And if you looked at the confusion matrix, then a lot of the mistakes could be attributed to other classes that fall within the same superclass. So there is some hierarchy that appears from the confusion matrix. So now, how can we learn dense representations to tackle, for example, semantic segmentation or semantic object segmentation or even INSAIT segmentation? So one direction that we explored was first leveraging classical computer vision priors like mid-level visual priors such as saliency estimators, optical flow, and also more like low-level visual priors such as superpixels and edge detectors. For this, we actually primarily relied on a self-supervised saliency estimator for the Pascal-Vogt dataset. And then we do the exact same thing. We incorporate this information into the contrastive loss, and we can learn dense representations. But of course, this approach has obvious limitations. So one of the downsides is that you are limited by the accuracy of these kind of region proposals that you're able to mine. So if you use edges or saliency, these have obvious flaws. So can we instead learn objectness or try to capture these objects or object information from these large-scale self-supervised models? And in fact, we can. So that's something that we tried. And our approach was, again, a two-step approach where we first leverage this self-supervised transformer. In this case, we compute an affinity graph between all the embeddings, and then we cluster this affinity graph using any type of method you might want to use, like normalized cuts or affinity clustering, etc. And then we bootstrap this information to train, or we bootstrap an instant segmentation model using these object proposals. And again, at scale, you expect that this is actually a valuable learning signal, even though these masks are going to be noisy. And then you can extend this to semantic segmentation as well. So if you look at some of the examples, actually, we were able to detect these different objects, even on more scene-centric data sets. And also for semantic segmentation, we were able to link like horses, trains, cars, etc. Of course, there are still some limitations to this approach, like especially if you have overlapping instances, such as persons, because they have their representations are highly correlated, even in like a very powerful self-supervised model. That could lead to problems. But some recent models, like some state-of-the-art models, I think last at CFPR, there's a Cutler, which basically uses the same strategy, but they mimic also scene-centric images by using copy-paste augmentations. Maybe people that are familiar with detection, that's something that might sound familiar as well here. Okay. So what are the key insights is that you want to decouple representation learning and clustering to prevent the model from latching onto low-level image cues like color or texture. Then you also want to encode, or you can use these representation learning methods to encode spatially structured representations. That's something that we leverage for this intersegmentation model. And then we also harnessed nearest neighbors. So this can be a powerful tool to identify similar objects or images. And then also we discussed a little bit prior knowledge. So what is the impact of dataset biases, invariances, and grouping priors on these representations? Okay, so now at INSAIT, I'm primarily focusing on generative learning and multimodal learning. So if people are interested, feel free to reach out. And you can also find the code on GitHub for all these approaches. So yeah, thank you for your attention.
Thank you very much.
Can I ask a question?
Yeah. Yes.
So you use nearest neighbor
Yes.
somewhere in page 16 or 15.
I used it quite a few times.
One of the potential problem is that so if points are like dense in some region and sparse in another region, then the number of nearest neighbors k has to be changed depending on the region.
That's
so
true.
In practice, how do you choose k?
Well, we used we just did an ablation over different amounts of nearest neighbors, so we didn't take the distance into account in our case, because that actually seems to work quite fine. But yeah, that's something that
global k does not really.
Yeah, we use a global k for different data sets as well, and that always seems to work quite fine. I think it was 20. You better choose quite a lot, so it can learn from its neighborhood. But I agree, it's also going to depend on the pretext tasks that you are using, like how dense they are going to be. But that seems to work quite fine in practice. Okay.
Thank you.
Okay, thank you for introduction. I'm very happy to be here to present my research work together with in the workshop. So actually, I'm working in RIKEN AIP. And my team is belong to a generic technology group. Our team work on the research basically for in the tensor method for machine learning. And in today's talk, I will present the overview of my team's work in the past years and also several latest work. So we are talking about efficient and robust machine learning with tensor network. As we know, one of the main trend of machine learning is foundation model, especially like large language model. It always costs a large scale data set. It needs a lot of high quality data set for the training of the model. And the model size are also increased dramatically. It has a huge models experience. Of course, it also costs a lot of computational resources. This is one example of a large language model. However, in the future, I think many applications, especially don't have high quality data set. So how to working on such applications without high quality data, or the data is not so much. And second is the application want to work on the IoT devices with very energy efficient. So such huge model is very difficult to deploy on such edge devices. And of course, the computation, like training time and the inference time, we want to have more efficient. So one perspective is from the data perspective. The data is not always complete and always high quality. In some application, like recommender system, we only have one data set with several different domains and very sparse observations. In such cases, it's very difficult to apply the neural network, which need a lot of training samples. And second, some other cases like image or satellite image or graph, the data is not complete, or the data is corrupted by the cloud or other noises. So one way is to, like, if we have many training samples, we can train a more robust model. But in some cases, if the data is very limited, like we only have one image with such cloud, how to reconstruct the original image and how to have more high quality data is very important. So our idea is to use the data intrinsic structure to help our learning models. Another case of noises is artificial noises, which is adversary attack, which we found is more difficult to remove or more difficult to like denoising. For the model perspective, as we know that over-parameterized deep neural network can give us very remarkable performance, but there are some other limitations, like the model is very complex and contain a large number of parameters. It's very slow computation and for the training and the inference. At the same time, due to the model is very complex and difficult to understand, it's considered as a black box. So its lack of interpretability is another factor. We cannot interpret how the decision derives from the data point. Also, the model is the lack of robustness to the adversary attack compared to other not deep neural network models. So our goal is to how to develop a lightweight models while preserving the performance, the good performance, and also being the more robust and interpretable. Okay, at the beginning, we tried to use like data intrinsic structure to help to remove the to help handle the noisy case. One example is to using the matrix completion technique to remove perturbations. So the idea is if all the training data using the matrix completion to like random missing pixels, then reconstruct it. And after this, we train a neural network. Such a neural network has specific constraints, like data must be like low rankedness or something else. For the inference, any given data, if the data, even the data is adversary attacked, so we can use just very high level random missing pixels to try to remove perturbation, then keep the high classification accuracy. The assumption is like perturbation doesn't have good low rank structure, while our data may have very good low rank structure. So this is the key trick we want to implement leverage to remove perturbation, but actually it's still not very perfect. Another case is for the GNN, like we can create many GNN and we concatenate them together. Then we use low rank structure or tensor decomposition. We can try to remove poison attack. So the fundamental technique inside of these applications is tensor decomposition. So the tensor decomposition is, the task is how to learn from limited tensor entries to predict unobserved entries. So given one data point, which is a tensor or high order tensors, so there are only sparse observations. So how to create a model and training the model than to reconstruct the full tensor. This is a fundamental method we have applied. And the challenge is we want to have a very high data efficiency. That means we want to develop method which just need like 1% or very few elements to reconstruct the whole tensor data. And second, the algorithm need to be scalable and efficient. And also at the same time, we want to have theoretically guarantee for exact recovery. So to do this, we propose several, like in tensor case, we propose tensor-based, TSVD-based nuclear norm to impose some kind of low-rank structure on the transform domain, and several nuclear norms are proposed. Actually, we can use this to optimize our data to find the low-rank structure. And such a nuclear norm also we give like theoretical guarantee for the error bound and the exact recovery. Another general framework is like this. So given the data, we first to do the tensorization, and this tensorization can be considered as any linear transformation or even nonlinear transformation. Because sometimes the data itself is not satisfy very good low-rank structure or for the tensor decomposition or tensor method. So we can use transformation. And after this, we use powerful tensor network methods for representing such data. And finally, we can reconstruct the data. And this is our optimization part. So we can optimize the fitting error on the observed point. And the assumption is after transformation, the data satisfy a specific tensor network representation. And to encourage low-rank structure or low-rank needs, we impose different definition of tensor nuclear norm on the tensor cores. So this is just a general framework, then like how to define the tensor nuclear norm on cores and which tensor network we need to choose. And also the tensorization, how to define the transformation. There are many different ways to do such work. So what's the tensor network? Actually, tensor network is a natural extension of matrix factorization and the tensor factorization to very high order tensor case. Because in the n-order tensor case, the tensor network is much more flexible than tensor factorization in three order cases. And in the, even in the quantum physics, they use tensor network to model the quantum entanglement function or many-modi functions. So tensor network is very good at very high dimensional data or high dimensional functions, and we can model more more flexible structures or interactions inside of the data or inside of the function. Okay, this is one particular tensor network model, which is similar to tensor decomposition. So we can represent n-order tensor as a tensor ring structure. And in this tensor ring structure, each node is a small tensors. So our goal is to represent these high order tensors by using many small low order tensors. And each core tensors have very small size, and totally they can represent such large data. And here is the link between the core tensors is the rank. So if the data has a very good tensor ring structure, the rank usually is very small. And to understand the tensor ring structure, actually in mathematics, is a sequential product of sequential matrix with the trace operation. So in the most tensor decomposition methods, there are still many big limitations. This is all tensor decomposition method based on the model. First, we need to give the likelihood function, which means how the data generated from latent factors if this is Gaussian distribution, then we assume there is some Gaussian noises. And this is one constraint. And the second is structure constraint, because depending on your tensor decomposition model or tensor network model you choose, you need to define explicitly how to operate in the latent space to generate the data. So in this case, if some data is satisfy good structure, then we can get good performance, but not always have good performance. So then we want to change these assumptions to be more relaxed. So we want to relax this assumption for likelihood function, and also relaxation of assumption of structure. Because in the real applications, the distribution is usually unknown. And also there are some complex trajectory or complex data structures. We don't know which structure is most suitable. So to do this, we design a new type of probability models for tensor decomposition. Instead of conditional distribution of data, and we use joint energy function or joint distribution functions. We define this joint distribution function is approximate to exponentially of this energy function. Then if we relax this energy function to be more like flexible, then we can model any distributions. But such model is very difficult to learn. So we borrow the constructive learning ideas, and we finally define this loss function to make this problem solvable. The big problem is we cannot estimate the marginal likelihood function by using traditional method, and using such self-supervised learning technique. Finally, we only need to calculate the joint energy function. Okay, this is some experiment to demonstrate our new tensor decomposition framework is able to handle different distribution for data observations, and also has some good performance on tensor completion task. So another case is if our data is not like a single data point or one tensors, but we still apply like a neural network model, especially in multimodal learning. We found like if the data is noisy or incomplete, and we can also use the tensor technique to improve our current multimodal learning. The assumption is along the time series data, if the data is clean and such data satisfy low rank structure, while if the data is incomplete or data is noisy, the low rank structure will be destroyed. So in this case, we can apply the low rank like tensor nuclear norm as a regulator on the latent space or the latent representations in the neural network models, instead of just apply such regulator on the data itself. And finally, we found such low rank regulator can improve robustness to like imperfect data, which is mostly we consider noise data and incomplete data. And the second part, we will introduce parameter efficient modeling using tensor network. One task is model compression. I think there are already several techniques to do model compression. And here we introduce the one technique which mostly based on low rank structure. And the idea is the weight matrix W can be represented by some kind of tensor network structure, which is more than standard low rank matrix approximation, because compression rate is in generally much better than low rank matrix approximation. And based on this, we can also do all the operation based on tensor network operation to insight to the neural network models. And another task is for multimodal learning, because it's very important for foundation models and to handle the image and the text together. So here, if we have multimodal data type, one technique is using tensor operation to enhance the model expressiveness, which is one kind of multimodal fusion technique. But such technique will generate problem of the dimensional increasing and complexity. So we proposed an extension of such tensor fusion technique. So we consider using tensor product of the representations with itself. That means tensor product with itself for p times, which can capture more information, not only for the interaction within the data features and also interactions between different modality. And in addition, also the high order polynomial functions can be captured. But this cases, the dimension will be increased significantly, as similar to the standard tensor fusion. So next, we use tensor network for the weight parameters W, and we found that after some kind of derivations, we found finally we can use tensor network operations to do this procedure, and the number of parameters doesn't increase much, which is only linearly increased. But such multimodal fusion technique can improve the model capacity and expressiveness dramatically. And similarly, we changed the recurrent neural network using tensor network technique. So we can formulate each layers as the tensor network operators with the tensor network representation of weight. And finally, we have such kind of layers. It should be noted that here we remove the nonlinear activation function. Instead, we use this high order tensor product to do the nonlinear function. And finally, we say that if this high order P will be large, it will generate a long memory, and small p will generate a short memory. That means our model will be more, expressiveness is much more better than the standard RNN, but without increasing any number of parameters. So next, because we use tensor network a lot in different models and different structures, but for tensor network itself, there are many hyperparameters, like how to choose tensor network rank and how to choose the order of tensor network. That means each node, the order changed, actually the results changed a lot. Also, the tensor network topology are different. Maybe some data is more satisfied with this tensor ring, some data is more suitable to use tensor chain. So this problem is also very difficult to solve because it's a high dimensional cases and a discrete optimization. And recently we developed several algorithms to solve each problem. Due to the time limit, I will skip the details for this. And next, we will talk about the robustness of neural network models when we use tensor methods for modeling the parameters. So first, we considered the two neural networks. One is standard neural network with just one fully connected layer with ReLU activation function. And another one is based on tensor layer, T-product layer. So the difference is here we use the tensor T-product operations, which is some kind of tensor, I think tensor SVD method based on operations. And here we basically study in theoretically to give the error bound of generalization error bound. And we see that in standard case, the generalization gap are similar to standard neural network, which is size independent. That means the error bound doesn't relate to the size of parameters. But in adversary training case setting, we realize that the error bound is related to the number of parameters. Basically the bound scales like this. So this is the DL -1 DL is the size of parameters in each layer, and there are L layers. This is the total parameters. So that means if there are more layers or more over parameterizations, more parameters, this error bound will become bigger. So the next, how to make this model more robust, and we consider if the low rank needs or low rank tensor structure can help. So finally, we found that if we impose the low rank structure, our error bound will become from this DL -1 multiple DL to in this form. That means we can improve this error bound by using the low rank needs on the weight parameters. And this is a simple simulations to show that it's actually is similar to our theory result. Of course, in real well-trained models, the parameters may not be exactly low rank, and we found that if we use a gradient flow method to train the model, usually we will only generate the approximate low rank case, not exactly low rank case. So next, we also study if the data is approximately low rank and how is the generalization gap looks like. Actually, the result in theoretically is similar. And even if your data is like a singular value is decayed in a polynomial patterns, we can even remove this rank R from the rank R to just remove it. We can further improve robustness. So in summary, tensor network maybe it's a powerful tools to like handle the data, high dimensional data, by incorporating the structure inside of data point or inside each data samples. And the tensor network can be also useful for modeling the neural network models for efficient parameters. But there are still many problems, like a tensor network itself, how to choose the best network structure, or tensor network permutation or rank is one big problem. And also we are very curious about if tensor network technique applied to neural network can be helpful for robustness to adversary attack or interpretability of neural network. And another future potential direction is quantum machine learning, and we already chat with many quantum people. I think they are very interesting in the tensor network to modeling the classical data to be the quantum state or qubit data, or using tensor network for quantum circuit. I think this is one potential direction we will work on in the future. Okay, I think due to the time limit, thank you very much. This is the end of my talk.
I had a question on several questions actually, but let me do one because we don't have so much time. So this NeurIFS paper, right, 2023, I talked about. So is there work on certification of tensor networks, like proving that absence of adversarial examples, for instance? I haven't.
You mean this one?
No, this work doesn't do this, but I don't know if there is work on like taking a tensor network and then proving that certain input point, high dimensional input point, cannot be attacked. So for instance, adversarial training of the tensor network and then proving some property of the input. Are you aware of this kind of research, or?
I think our research is based on these two models. One is like a very simple model. This is just one layer, and this is a tensor network model.
Right, that's fine, yeah.
Yeah, and we try to study the generalization gap under standard training case and adversarial training case.
That's right, yes.
Yeah, I think both of them can be attacked by adversarial attack. It can be attacked, but we are wondering how this generalization gap changes when we use tensor network and when we don't use tensor network.
Yeah, I guess what I'm saying is I haven't seen work on which could be interesting to look at certification of tensor networks, meaning that you certify local robustness of tensor networks. So you take inputs and then you prove that the input cannot be attacked up to some norm, for instance, like L2, L infinity or whatnot. So there's lots of work on this in the standard networks, but I haven't seen it in the tensor networks.
I see. Yeah, it could be a very interesting direction. But in this study, we don't work on certifiable or certificate.
I see this. This could be interesting.
Yeah, that's a very important direction.
Yeah, that could be. Because I don't know. It's like, are the tensor networks with this generalization gap? Are the tensor, because you said you look at normal networks and tensor networks? Are the tensor networks like inherently more robust, or there's some results there versus the standard networks, or what's your thought?
Yeah, for standard neural network, I think there are theoretical results. But for tensorized neural network, I think this theoretical result is quite new. Maybe the first work.
No, I was just wondering how they compare in terms of robustness.
Can you give some interpretation of the theorem?
Yeah, maybe like what is there? Are tensor networks maybe inherently more robust or not?
Yeah, from here, I think the big point, important point is low rank needs. If our weight parameters without low rank, the scales looks like this, and with low rank needs, the scales look like this. So from the multiplication of DL minus 1 DL becomes a sum. So this is just the size of the weight parameters. So yeah, if we use low rank needs, this part will be smaller. For example, if the rank is 1, this weight is just a rank 1 matrix or rank 1 tensor, then our error bound will be from the multiplication to the summation.
So does this mean that you can use deeper networks that would have the robustness properties of shallower networks? Is that what you're trying to say with this theorem?
Yeah, we want to say under the first condition is the model must be over parameterization. That means you have a lot of parameters for your model. A second message is we want to emphasize if we impose low rank needs on the weight parameters in the tensor network, then the robustness error bound will be smaller.
But this is more like an effective number of parameters.
No, it's fine.
Yeah, effective number of parameters. Yeah.
Okay, yeah, that's interesting how this relates with the inherent robustness.
Yeah.
We need to look at.
However, currently we focus on this theoretical research result. We haven't do much experiment for real practical examples or practical results. This is just one simple example. Next step, we will evaluate in a lot of the like a promising data set or big data set for experiments.
Yeah, that for us is very interesting, at least certain groups on the adversarial robustness and especially certification, like proving with things like randomized smoothing or complex relaxation. So we can chat more, I think.
I think some of us can meet at New Rips.
Yeah. If whoever is coming. Are you going to New Rips?
Yes, we can meet in the New Rips.
Yeah. Great. Okay.
Thank you for the question.
Thank you very much for a nice talk.
Thank you for the introduction. I'll talk about incentivizing collaboration in federated learning. I was already introduced, so I can say what our group works on. So we focus on guarantees for machine learning. So this would hopefully make ML more trustworthy. And some topics that we work on are collaborative learning, power distribution generalization, performative classification, robust machine learning, and others. And in terms of techniques, we're interested in statistical back learning, game theory, optimization, and other theoretical tools for ML. So this talk would be about collaborative learning. And I'll first try to explain and motivate why participating in federated learning can be a difficult choice. Basically, should you or should you not participate can be tricky. And then after that, I'll explain how one can go about incentivizing cooperation in collaborative federated learning. So moving to the first part, I think that it's easy to motivate why collaborative learning is useful. So nowadays, machine learning models need a lot of data to be trained well, and such data can be expensive to obtain. So it often makes sense to gather data from multiple data sources. So, for example, if some online platforms would share data with each other, then they can probably offer better user experience. Another example is laboratories in science. So in science, it is extremely expensive to obtain data, often in physics and chemistry, let's say. And it would definitely make sense for laboratories to work together and to build better machine learning models for science through collaboration. And finally, a canonical example is federated learning, where you might want to use data that is distributed on all kinds of private devices like mobile phones or laptops, and to train on the union of this data in such a way that you obtain very powerful models. So one issue is that you could be worried about sending your data to the server, right? Basically, like this is personal data, but luckily there is the concept of federated learning, which allows for distributed training of machine learning models, so the clients never send their data to the server. So how this is achieved is with a simple observation that if the server sends the model to the clients, then they can just return the gradient of their data with respect to the current machine learning model. And this is everything that the server needs to actually update the model with SGD. So presumably this is more private because these gradient updates are not the actual data, so the data is never sent. So this sounds wonderful. Now we can train machine learning models with giant data sets, many clients participating, but in practice there is multiple risks that also come with collaborative learning. So the first one is privacy. Well, although, as I mentioned, we send gradients, it has been shown that in some cases you can actually read off or partially read off data from these gradient updates. So although some defenses exist, in general, there are certain risks that you should take into account if you were to participate in federated learning. And the second aspect, or at least a second aspect, is competition. So very often the people or companies that have data like yours are competitors on some downstream tasks. So I mentioned this example about the online platforms. So yes, they can get better models and they work together, but on the other hand, they do compete with each other on the market. So it's unclear whether this actually makes sense for them. So in some of our recent work, we've been looking at understanding when two firms and entities have an interest in participating in federated learning. So we have some ongoing work on privacy incentives, but in this talk, I'll focus mostly on the competition aspect, which I'll present next. So this is joint work with Nikita, who is here and is a PhD student with me. And it will appear at NeurIPS this year. So as I already mentioned, it's very often exactly your competitors that have interesting data for you. So you can easily think of 2 or more companies that have their own data, and now they face this dilemma whether they should work together or not in building machine learning models. So it could be that they just agree to share data with each other, or it could be that they work in some federated learning way to preserve the privacy. So if they don't share data, this is just what normally happens, they just work on their own. So then they can get less good machine learning models. But on the other hand, then they're not worried about helping their competitors. And in the case when they do share data or participate in federated learning, then they can obtain better machine learning models. So then this can improve their services or optimize their production costs. But on the other hand, this would also be the case for their competitors. So for this reason, it's not clear immediately whether it's actually beneficial to share data or not, and in which situations is it beneficial. So to answer this, we model each of the components in this decision-making process individually. So we model the aspect of data sharing. So basically, how do the firms negotiate and bargain on the data sharing process via a collaboration scheme? We model the impact of data on the quality of machine learning, and then later on the production costs and other characteristics of the companies through a data impact model. And finally, to describe the competition between firms and their interactions on the market, we use a market model. So in this general framework, not much more can be said, and this is why we also consider a specific example now in the paper also. So for the collaboration scheme, basically, let's focus now on 2 firms. So there is 2 firms, and we postulate that they would agree to share data if and only if both of them expect that their profits would increase. So if at least one of the companies doesn't think that they benefit, then they don't do it. They cannot agree. So that's quite natural. The data impact model, this is basically just inspired by learning theory and optimization bounds. So if you get more data, then it's well known how the guarantees on your machine learning models evolve. So this describes basically how does the data impact your machine learning quality. And an important parameter here, beta, is basically the easiness of the learning tasks. So some learning tasks are easier, others are harder, and beta corresponds to how easy your learning task is. And finally, there is the market model. So we just take a classic market model that I will not cover, which is an oligopolistic market model. So this just means that the firms have enough power to influence the market prices and compete over some pool of customers to sell more goods. And so there, an important parameter is how similar the products of the companies are. This is gamma. So this effectively measures how competitive the market is. So if the products are more similar, then there is more competition between them. And so then what we prove is that collaboration makes sense and would occur if and only if both of the companies have a sufficiently high proportion of all of the data pool. So basically, the big company is going to agree to share data with the smaller one, if and only if the fraction of data that is in the small company is still relatively large. And the threshold here is the important aspect, basically how does it depend on the model. So it depends on both gamma and beta through, so it's increasing in both of these parameters. So this basically means that if you have an easier learning task, so beta is larger, then it's harder to agree on collaboration because basically you can do better with your own data. Anyway, this is a easy learning task.
Do you know the function x explicitly?
Actually not. We can have some approximate versions, but we know that it exists, and we can prove that it's increasing. But I think that closed form is not possible. Not analytic closed form is not possible. Yeah. So then there is also gamma. So if the company's products are more similar, so if the competition is more intense, then naturally it's less likely they would agree to collaborate. And we also confirm this through simulations when you have many companies. Basically, the y-axis is the inverse of the size. Is the size of the average coalitions that form. So basically, this is inverse of the likeliness they would agree to collaborate in some sense, and is decreasing with gamma and beta. So effectively, once again, the competition and the easiness of the learning tasks are directly impacting the likeliness for collaboration. Okay, so I hope that I've convinced you that in general, it's not obvious whether entities have an interest in joining federated learning. And in particular, it could be that in some cases, such incentives are lacking. So then you could say that this is no big deal because if they don't have interest, then they'll just not do it. But on the other hand, if they do have some conflicting incentives, then there is also the risk of having some clients basically cheating and manipulating the protocol in order to sabotage others. So this is classically modeled in the literature as a Byzantine robustness problem. So this basically means that we consider a distributed training protocol with n machines, and a subset of them is adversarial, like this guy. And so basically then they can do anything to manipulate their messages and damage the learning process. And it has been shown by other people that in case of convex Gauss functions, if a learning algorithm can guarantee a certain accuracy, then it must be that it has taken a certain number of steps. And unfortunately, this number is nasty because of this term. So this term doesn't depend on the number of participants. So this result basically tells you that if you want to be accurate in such an adversarial setup, then you should take almost as many steps as if you were working on your own with only one client. So this is not good because there is no benefits from collaboration. And you could ask whether this is an issue of communication or exactly this HGD implementation. But in fact, in earlier work of mine, I've shown that this is also a statistical hardness problem. Basically, there is no learning algorithm with access to all data in a centralized manner that can overcome this type of corruptions. So this is why it's important to incentivize clients to share data honestly. And this is what we have looked at with in collaboration with Martin at with Florian, who is a master student, who was a master student at ETH, now at Max Planck, and also with Georgi, who is a high school student and is part of our high school program at INSAIT, where we work with talented high school students on real-world science problems, and then they publish a paper at New Leaves. So right now, let's think about federated learning as a game between many participants that are rational and try to incentivize them to contribute meaningfully. So we have players, they have some pi-ID data that is sampled from some distribution, and for simplicity, let's assume they have the same number of samples. And now they communicate to federated learning and seek to get good models, right? So this is basically the setup. Now, to make this a game, I should define, first of all, what are the actions that the players can take. So in general, they can attack through manipulating their messages. They can also defend through receiving messages, then being cautious about how they use them. So like this is what kind of they can do in this protocol. So then I should also tell you their rewards, which are basically just a function of all models in the general case. So their reward basically depends on their own model, but also on the models of the others. And I should also tell you that the players act as in game theory, so like namely rationally, meaning that they optimize their expected reward, and also strategically, meaning that they consider what others might do when they take their decisions. Okay, so this is the general framework. Now, how do we model competition within this framework? So like basically we have the same setup, and then we say that the players can attack, defend. So for simplicity, let's assume here that the attacks are only based on adding noise. So the alpha here basically measures how aggressively does participant manipulate their updates. In the paper, we also cover biases here for attacks, meaning also directed attacks. And then on the defense side, it turns out that it doesn't matter much mathematically whether you have defenses, but in general, the defenses we consider are basically weighting the local information with the global updates from the server in order to achieve some robustness to manipulations from the others. And so now the competition aspect basically gets encoded into the rewards. So the players want to get a good model themselves. So this means that they minimize their own loss. At the same time, they want that the others don't get good models. So they also try to maximize the losses of the other models. Okay, so like this is one way that you could model this competitive aspect in federated learning. And it's easy to see that in many cases, such games could actually not have nice equilibrium, meaning that in general, if a player is helping others by sending some messages, then they can avoid this help through just increasing their attack to infinity. So if they send nothing useful, then there's no way that anyone can benefit. And in the single round case, you can actually prove that there is no Nash equilibrium with the finite alpha here. Well, so like basically there is no Nash equilibrium. Okay, so now the question is, can we change the protocol in such a way that would disincentivize such behavior and encourage basically the participants to not cheat? So first of all, let's do mean estimation, which is the simple setup. So there is only one round. The clients have some data locally, and they want to estimate the mean of the data distribution mu that they don't know. So basically what they can do is they can send their empirical means to the server, then the server can aggregate the received messages and send back the aggregated message to the players. And so now it's easy to see that the players can increase their alpha here and damage messages, and at the same time they can correct for their own damage because it's a simple setup here. And so basically then they can win. Well, they cannot be an equilibrium that is nice because they can always increase the alpha. So to change that, what you can do is that you can request the server to not send them the mean of the messages, but a perturbed mean that is perturbed proportionally to the distance between the client update and the mean of the updates. So if a certain client sent an update that was very far from the mean of the others, then they basically get a low quality update. So then increasing the attack maybe doesn't make sense anymore. And in fact, this is what we proved. So we proved that the Nash equilibrium here in the simple setup is exactly the honesty where they use alpha equals 0, so they basically don't corrupt the update. And in particular, then the quality of all learned models is the statistically optimal because there was basically no corruption. And in particular, now they also benefit from the collaboration. So this was the simple mean estimation setup. So finally, the HGD case. So if you have HGD training for T rounds on a strongly convex Lipschitz and smooth function on a bounded domain, so a classic setup in optimization. So then, instead of this modification here, what you can do is that at each time step, you can add a penalty to the players that is proportional to how far they were from the mean of the updates at this round. So for this scheme, what we can prove is the following. So first of all, at any Nash equilibrium, the server's model, so the centralized model, is close to optimal in a theory optimal ways. So basically, this is the rates you expect when the clients contribute clean data. So it's almost as good as clean training, basically. Secondly, the honest players don't pay in expectation. So if you're honest, then your penalty from here is in expectation 0. And finally, the players are incentivized to participate in the sense that the rewards that they get, despite the penalties, are larger than if they just work on their own. So this actually means that they're incentivized to participate. They win more. So this was it. I hope that I convinced you that joining federated learning is a difficult choice. And in some cases, if the clients don't have this incentive, then this can lead to trouble. But on the other hand, if you cleverly model the incentives, then you can design schemes that can enable honest training and thus bring benefits from collaboration. Thank you.
So nice talk. Any questions?
Yeah. So basically, the kind of take-home message is that if you have a large number of collaborators, then things are good.
Well, so assuming that your model of incentives and behavior is good, yes. So basically, yeah. So like in this case, definitely. Basically, when we have this type of a setup, then it is true that if you have more and more players, then you find like you would converge to optimal. And I should also say, I briefly mentioned that we also do work on the privacy aspect here. This is work in progress, but in the privacy case, if you consider incentives that trade off accuracy guarantees with privacy guarantees, then we can also prove that in the limit of infinite number of players, it's always possible to design a protocol that is beneficial to everyone. So it's mutually beneficial.
On the other hand, you can also consider some special scenarios where if you have more clients, maybe the performance is deteriorated, something like that.
I guess that is so first of all, if you don't do any modifications to the learning algorithm, then in general, it is very likely that the equilibrium will be much worse. I don't know whether it's always possible to find an algorithm that incentivizes better behavior than in the single learning case. This is probably not so. This is not obvious, but I think it's quite an interesting.
So I'm curious, like the borderline between two cases, like having more clients is better, having less clients is worse. There must be some borderline,
Yeah. So in the privacy case, definitely, if a client is extremely keen on privacy, then you have to allow them to have lots of noise, because otherwise they will not be happy with the privacy that they get. So in this case, then they could damage the learning algorithm. And so then maybe it does make sense to exclude a subset of the clients in order to make the others more happy. So if you have some metric of global welfare of everyone, let's say, then you could optimize for this. But in general, yeah, like the question of whether you can always construct an algorithm that at the equilibrium benefits everyone is, I think, quite interesting and quite tricky. Yeah.
And have you ever observed any, I can say, kind of phase shift if you have more clients, the property changes in a strange way?
Yeah, so actually in the privacy paper that I mentioned, this is under submission to AI stats. So in this one, basically, there is a threshold of number of clients beyond which we can prove that. So it's an if and only if conditions for the existence of beneficial schemes for everyone. So like there is a cutoff beyond which basically you can provide a good machine learning algorithm that benefits everyone, and under that you cannot do it. Yeah, but it's still like relatively specific.
Something happens at that threshold.
Yeah, so it is just basically where the beyond which point
you get all like a proof artifact, or there is really something there.
I think well, so within the specific model of utilities and incentives that we consider, it's an exact result. So it's not a proof technique, but it's literally that it's an if and only condition in this separation. Yeah, so in this setup, yeah.
Thank you very much.
Thank you also for the nice questions.
So my question was, this penalty that you're giving to clients, it also can affect disproportionately heterogeneous clients. So how is the trade-off between heterogeneity and essentially defending and incentivizing fair play?
No, this is a great question. So this is something that we have been thinking about. So in this model, we consider high ID data. So everyone has the same distribution. As soon as you introduce the heterogeneity, then there is an additional layer of incentives that comes in, because everyone wants a good model on their own distribution, not on the other's distributions, right? Why would they care? So basically, already just the heterogeneity, even without any competition aspect, brings this conflicting incentives, and this is super interesting to look at. We have, so like Nikita wrote one model of this, but we have not yet managed to study in depth. Actually, we do have some heterogeneity we can cover here, but we still assume that they care about the global distribution rather than the individual ones. But if they care about the individual ones, then the incentives are conflicting, and it's quite interesting and tricky. Thanks.
Okay, great. So
thank you
for a nice talk again.
Okay, thank you for introduction. My name is Sakuma from RIKEN AIP. So today I'd like to talk about reliability of explainable AI. And also I'd like to say thank you to giving me a chance to give a talk this wonderful workshop. So let me introduce my team. So my team is AI security and privacy team. And basically, our team topic is broad, including technologies related to AI and AI responsibility. And it covers like attack and defense for AI, privacy of AI, fairness of AI, and explainable AI. And today, my topic is about explainability. So specifically, this talk has two messages. One is I'd like to introduce several recent results about explainable AI of our team. And also recently I'm thinking, does explainable mean really responsible? So I'd like to give the talk about these two topics. So first, let me explain what is explanation. So let's say we have some classification model that gives classification result. And when we say the classification model is explainable, in addition to the classification result, the model gives some certain form of explanation. So what is explanation? So there's no firm definition, but here explanation is considered as auxiliary information that justifies classification. And we expect that the classification result becomes more reliable than receiving only classification results. So if the classification model, if the process of classification model is simple, giving explanation is almost obvious problem. So for example, when the model is linear regression, by investigating the coefficients of the model, we can justify the inference result. And also when the model is, for example, decision tree, by checking the decision path, why the inference result is given is obvious, and it's currently explainable. But when the model is complex, like neural network or gradient boosting trees, the classification process is not followable by humans. So what we can do for explanation is simply to extract a certain interpretable aspect of the inference process. So this would be the main issue of explainability. So I'm giving you some well-known example, the reason why explainability can be important. So given these four images, we have four classification results. So for this image, the result is horse. But for this image, the classification result is not horse. And for this one, the result is horse for some reason. And this is not horse. So what's happening here? So the reason is looking at the left bottom in detail, we can find some logo attached to the photo. So the neural network did not learn the object itself, but simply learn the logo. And unfortunately, in the training data set, this logo is attached to all host data. So for the neural network, it was much easier to use this logo to classify hosts. So this works as some shortcut for classification. And so with this logo, some images without host is classified as host by using this shortcut. So when real images are without this logo, when some host image without this logo is given to the model, of course, the neural network cannot recognize this as host. So this is called clever Hans phenomenon. And by checking why this classifier recognize this image as a host, we can see the neural network has obtained some wrong perception mechanism by looking at the attention of the classification. So this can be some examples that explainability is sometimes important. So one difficulty of explanation is that there is no de facto standard of explanation methodologies. So depending on who is going to have the explanation and depending on for what purpose the explanation is needed, the explanation methodology, the appropriate explanation methodology would be changing, like feature attribution and explanation by sample, explanation by natural language, explanation by counterfactors, and explanation by interpretable concept. So I'd like to introduce a couple of recent results of our team. So the GradCam is one of the most well-known explanation method. So the concept is like given some image, the GradCam shows the why the image is classified. The GradCam gives some region in the image to justify the classification result. So in this case, the classification result is cat, and the GradCam shows the GradCam highlights the region that AI focuses on to justify the classification result. So our team utilizes the GradCam for malware functional analysis. So usually malware is created in such a way that its function is not easily analyzed because the malware is designed for some malicious intention. So its stealthiness is important from the perspective of attackers. So in that sense, the creation of malware is easy, while because of its stealthiness, its analysis is very much labor intensive and time consuming. So for the practitioners, it is required that analyzing the functionality of malware needs to be more efficient. So our idea is that this kind of explainable AI could help the practitioners to analyze the functionality of malware. So the idea is first we represent the malware binaries as images, and we trained the malware classifier based on the images. Then we apply the GradCam to indicate in which region helps to classify malware types. And after having this kind of attention, by reverse engineering the code of the malware binaries to identify which functionality is implemented at the region the attention indicates, which helps to quickly identify the functionality of malwares. So this is an example of analysis example of some malware called Win32 Gaobot. And this Gaobot is known to attack on the user devices to steal password of PayPal and send the information related to PayPal access to some malicious server. And this is a malware binary represented by images. and the right image shows the attention. Here is the red part, yellow part, green part are some regions that is used to classify this malware. And by analyzing the code corresponding to this region, we could find out that this region represents some functionality for connecting to IRC server, and the yellow part represent some functionality for redirecting packets to a specified address for DDoS attack. And the green part is important one. So this encodes some functionality for checking whether string paper is contained in the contents of the intercepted HTTP communication. So by focusing on these code parts, the practitioners can efficiently analyze the functionality of the malware binaries whose functionality is unknown. And another explanation method is a conceptual explanation. So this figure illustrates the information flow of conceptual explanation. First, using some feature extractor, the concept contained in this image is extracted. So in this case, this is a bird image, and the feature extractor is trained so that it extracts some features related to identify bird species, such as wing color, undertail color, beak length, and so on and so forth. And using these extracted latent variables, some interpretable models, such as linear regression or decision tree, is used to identify bird species. So what's nice here is the first half is not explainable since this is a neural network, but the latter half, after extracting concepts, each concept corresponds to some semantic meaning, and these concepts are used to identify the bird species using some interpretable model. So the latter half can be interpretable. So this kind of explanation gives explanation like this bird is classified as some class because wing color is black and head color is yellow, like that. So this fits to our intuition and very nice. But one limitation of this model is that to have these kinds of concepts in the training data, we need to have some concept labels. So usually we don't have that kind of concept labels in a training data set. So how we can overcome this problem can be some challenge. So this is our recent result, unsupervised visual concept extraction. So as I said, when we use some concept-based explanation, we need some concept levels in a training dataset. So this method allows us to extract some visual concepts, without having concept levels. So the idea is that basically we use a variational autoencoder. And so we use the latent variables for concept-based explanation. And to give some semantic meaning to the latent factors, we introduced some regularizer. One is to make the concept visually simple, and the other is makes the latent variables causal to the classification result. By doing that, by changing the value of latent factor, due to the effect of the last term, the classification result is the classification result changes like E and F. And due to the effect of the second regularizer, the changes in the visual changes by switching the latent variable becomes understandable and simple. So this is a result of the resulting concept. For example, by changing the first latent variable, the bottom stroke disappear, and by switching this latent variable, the letter changes from E to F. And for the second latent variable, corresponds to the presence or absence of the middle stroke. So which distinguishes the letter E and letter C. And the third one corresponds to the presence or absence of right stroke. So by changing the value of the third latent variable, the letter changes E to B. So using these concepts, we can give explanation like this letter is classified as B because there exists a bottom stroke, and also there exists a middle stroke, and the right stroke is absent. So this kind of explanation is possible visually using this technique. Also, this is still under review, but we presented some unsupervised textual concept extraction. So this is an application example of classifying 5 yellow flowers. So here we, as an interpretable model, we use decision tree. And here the concept is we introduce some phrase of natural language for the rules of each node. So for example, this node has a phrase, dark orange petal. And in the process of inference, we measure the distance between the given phrase and each picture. And if the distance is small, for example, the decision path goes left, otherwise goes right. And so by determining phrases for each node, we can explain the reason why some image is classified as, for example, buttercup by following each phrase by connecting each phrase along the decision path. So how we can find this kind of phrase is our proposal. So here we use some language model and finds the appropriate phrase in natural language by doing some optimization over the latent variables of the language model, so that the classification result is improved. And at the same time, the phrase is not too much complicated. So now I introduce several explanation methods. And now I'd like to discuss the relationship between explanation and responsibility of AI. So of course, explainability of AI will help make AI more responsible. However, there are several cases where the explanation itself is not that reliable, as listed here. So we look each case in turn. So the first case is the explanation method itself is sometimes problematic. So in this figure, this is actually the saliency map of some neural network, and here several different kinds of the saliency map is shown, and from left to right, the model parameters are randomized. So when the model parameter is randomized, of course, the model gives random prediction. So the explanation result itself should be also randomized. But what we see here, what we see here is, for example, in case of guided back propagation, even after model parameter randomization, the explanation does not change a lot, which means that the explanation by this method is not depending on the data, not depending on the model, but simply it works as a certain kind of filter. So, meaning the explanation by this method is not that reliable. So this example shows that explainability itself does not necessarily mean responsibility. And also, this is an example of attack on explanation method. So I think everyone knows about the concept of adversary example. And this is a variant of adversary example where the target is not the prediction label, but its explanation. So here, adversary perturbation is injected into the image so that the explanation is manipulated in a way that the adversary wants. So if the explanation method is manipulated by adversaries, of course, the explanation itself is not reliable. And here is the case where the concept-based explanation is not that reliable. So in this case, we consider some conceptual explanation of gender from facial images. And here the concepts are like blonde hair, heavy makeup, wearing earrings, and so on and so forth. And after extracting concepts, the gender is determined by some linear classifier. And this color map shows the intensity of the coefficients of linear model. And looking at the result, we can find that some attributes that should not be correlated to the gender identification has large coefficients. For example, chubby or bags under eyes, gray hair, baby hair, blurry. These are, of course, not related to the gender, but in the resulting model, these attributes has large coefficient in a linear model. So in this sense, the resulting model is not appropriate to give good explanation. So to cope with this kind of problem, we presented some statistically significant concept-based explanation. So the problem with conceptual explanation with these kinds of latent variables is that when the concepts are extracted from data, data are sometimes biased. So even when the concept itself is not related to the target level, the concept can be associating with labels to some extent. So even if we use some sparse model like Lasso, linear models employ unnecessary many factors as an important concept, which causes false explanation. So what we did for this problem is to introduce some sparse feature extraction method, considering that the feature is used as a feature. And also we introduced some knockoff to suppress the false discovery rate. And by using that, we could show that the proposal method can suppress unnecessary concepts that is not appropriate for example, gender identification. So this is a last example. The explanation required by human and explanation that AI thinks it's reasonable are often different. So in case of human's decision, the decision should be justified with background knowledge of the domain. For example, this image is horse because it has four long legs and something like that. But in case of AI's decision, since AI generates its explanation depending on its training data. So if the training data had some unexpected bias, its explanation is also biased, like as I introduced in the horse classification example. So this is one example that this kind of gap arises. So now our team is dealing with the classification of medical images of malignant lymphoma. And I don't get into the detail of the characteristic of a problem, but what we need to focus on is the cell types and the distribution of cells to identify the subtypes of this kind of cancer. And usually for this kind of classification, GradCam or saliency map is used for explanation. But since identifying subtypes of this kind of disease, we needed to focus on each cell type and the distribution of cells. This kind of highlighting the region not appropriately works. So what now we're doing is constructing cell graph and we are trying to construct some classification model using the cell graphs. And this is some initial result. And we picked up several representative types of cells and investigated the relationship between the different types of cells. And using that, we can attain a very good prediction accuracy, like 82%. And we got comments from pathologists that the prediction accuracy itself is good, while the explanation we can get from the result is not convincing. So in this case, the relationship between cluster 7 and cluster 17 is useful for prediction, but the pathologist says that I can't understand why the relationship between these cells are important for prediction. So that is far apart from the pathological background. So there is still a gap between the justification by AI and justification human. So this is the last slide. So we want that AI is highly reliable, and for that we need some explanation to justify the inference. While if the explanation itself is not reliable, the AI cannot be reliable. So in conclusion, the message is simply the explainability itself is not that important, while how the explainability is reliable would be important, like statistical significance or compatibility with domain knowledge or robustness against environment changing and attacks. Okay, thank you so much.